where we could say that f is not differentiable at a number x is equal a. So we say here we have three cases of the function differentiable: everywhere, open interval, closed interval, and at a point. But when we can say this function is not differentiable at x is equal a. So here we go, where f fails to be differentiable, a function f fails to have a derivative at x is equal a if the first case, the function f is discontinuous at x is equal a. So if the function is not continuous at the point x is equal a, so it will be not differentiable. Then the second case, if the graph of f has a corner at a f of a. So if the function has a corner, for example, the absolute value function, at the point 0, 0, the graph has a corner, so we conclude that this function is not differentiable. And we have seen in section 2.7 that when we have absolute value of x, we said this function doesn't have a tangent line because the tangent line from left is different than the tangent line from right at x is equal 0. So this function has a corner, so it will be not differentiable at 0. Also, in addition, since the derivative gives the slope, f will fail to be differentiable at a point a f of a at which the tangent line to the graph is vertical. And we have seen example of this one for 2.7 when we have y is equal x1 over 3, where the tangent line was vertical tangent line, and we say this function doesn't have a slope. So here we have three cases where the function is not differentiable: if it is not continuous at a, if it has a corner, if it has a vertical tangent. So three cases you need to know it where the function is not differentiable with an example. إذا الفانكشن غير متصلة عند النقطة A، إذا الفانكشن has a corner نفس اللي هي absolute value of x، إذا الفانكشن has a vertical tangent نفس ما قلنا اللي هي في الروت x أو في x over 1 over 3. So here we have example number 6. Let y is equal root of x. Find dy over dx when x is equal 9. Our function here is f of x is equal root of x, and we need to find the derivative when x is equal 9. So to find the derivative, we use the definition where f prime x will be equal limit of fx plus h minus f of x we divided by h when h approach to 0. So now let's substitute. F of x plus h will be root of x plus h minus f of x will be root of x divided by h, and we take the limit when h approach to 0. So now here if you use direct substitute, you will get it will be equal 0 over 0. So it's better to multiply by the conjugate, which is root of x plus h plus root of x, and we divide by root of x plus h plus root of x. Now we will simplify our function, so this will give us this equal limit root of x plus h multiplied by root of x plus h, it will be x plus h, minus root x multiplied by root x will be minus x, and this will be all divided by h multiplied by root of x plus h plus root of x. From here we can cancel x with minus x because they have different sign, one is positive, one is negative. So we left with limit of h over h root of x plus h plus root of x. Also we can cancel this h with this h, but we will do it in different steps. So it will be equal limit of h over h root of x plus h plus root of x. We take the limit when h approach to 0. We said we will cancel h with h, so these two h will cancel, so the result will be limit of 1 over root of x plus h plus root of x. We evaluate the limit when h approach to 0. So now replacing any h by 0, we get 1 over x plus 0 plus root of x, which will give us 1 over 2 root of x. So the derivative will be 1 over 2 root of x, but we asked to find if the derivative from x is equal 9. So the final step, just we need to replacing any x by 9. So here we have d over dx of f when x is equal 9 is equal 1 over 2 root 9. This will give us 1 over 2 multiplied by 3, which is 1 over 6. So the slope or the derivative of this function when x is equal 9, it is given by 1 over 6. Sorry, the slope will be 1 over 6. Example number 7, are the following functions differentiable at x is equal 0? We have f of x is equal absolute value of x, b g of x is equal the third root of x. So let us see the first one, f of x is equal root absolute value of x. We know that the graph of the absolute value function is given by this one, f of x is equal absolute value of x, and we said that the function is not differentiable if it has a corner, if it is not continuous, or the function has vertical tangent, either one of these three. So from the graph we see that this function has a corner at x is equal 0. So let us see if it is why it is not differentiable. Our function is f of x is equal absolute value of x, and we know that this absolute function is given by x if x greater than 0 and minus x if x less than 0. And we have seen that from the previous section, which is section 2.7, that the slope of any linear function will coincide with its tangent line. So that's mean the slope of the function. So here we will write f prime x will be just, so the derivative of x will be 1 because here we have the function y is equal x, so the m is equal 1, the slope is equal 1. When y is equal minus x, the slope will be equal minus 1. So here we have x when x greater than 0, when x less than 0. And the graph of the tangent line, or the graph of the slope, it will be 1 when x greater than 0. So here at the point 1, and minus 1 when x less than 0. So here we have minus 1. This is the graph of f prime x. So we have seen at 0, the tangent line from right will be equal 1 and the tangent line from left will be minus 1. So since it does not exist, we conclude that this function is not differentiable at 0 because it has a corner at the point 0, 0. So part A, f of x is equal absolute value of x, it is not differentiable at the point 0 because it has a corner. Let us see g of x is equal the third root of x. So this function here we have the graph of y is equal x1 over 3. The derivative of this function is given by 1 over 3x over 2 over 3. This function is continuous at 0 because it is clear from the graph, but f prime is not defined at the number, at that number. So at 0 the derivative is not defined because we cannot find f prime 0, because if you get 1 over 3 multiplied by 0, so it will be 3 multiplied by 0 will be 0, 1 over 0, so this will give us infinity. So we have seen that the limit of the derivative when x approach to 0 from both sides will be equal infinity, because this function has a vertical tangent line at x is equal 0. So since this function has a vertical tangent line, we conclude this function is not differentiable at the point 0, 0. Why it is not differentiable? Because if you find the derivative, then you replace x by 0, will get 1 over 0, which is infinity. Since the limit of the derivative, not the function, the limit of the derivative from both sides it goes to infinity, that means your function is not differentiable at 0 because it has a vertical tangent. Also, the graph of function f can have all a vertical tangent at the point a f of a if f is differentiable only on one side of f of a, is continuous from the left to right at a, and either the derivative absolute value of f prime x goes to infinity as x approach to a from left, or the absolute value of f prime when x approach to infinity as x approach to a from right. So here we have seen that the function has a vertical tangent where the derivative at 0 from both sides it is infinity. Here it said that also the function may have a vertical tangent if it is differentiable only on one side. For example, if we have the function root of x, at the point x is equal 0, this function is defined only when x greater than or equal to 0. So just we can take it from one side, x approach to 0 from right. So if the derivative when x approach to 0, when x approach to a from left is equal to infinity, or the derivative goes to infinity as x approach to a from right only, we conclude this function has a vertical tangent. يعني ما لازم الفيرتيكال tangent إنه لما نجيب الديريفيتيف ونجيب الليمت أنت يطلع لي من الصوبين انفينيتي، لا، إذا كان بس من صوب واحد نفس الشيء نقول إن الفانكشن has a vertical tangent. So last theorem in this section, which is the only theorem here, theorem 3.1. If f is differentiable at a number a, then f is continuous at a. So if your function is differentiable, that's guarantee it will be continuous at a. But the continuity does not imply differentiability. So if the function continuous, if the function differentiable, it will be continuous. But if the function continuous, that doesn't mean that the function is differentiable. Let us see this example. So we say that if our function is continuous, if our function is differentiable, that means it will be continuous. But if our function continuous, that doesn't imply that our function is differentiable. Why? Because we have seen that if the function differentiable, it should be continuous, because we said the function is not differentiable if it is not continuous at a point. But if the function continuous, doesn't that mean the function differentiable? So here we say no. Why? We have an example, absolute value of x. So when we say this one is absolute value of x, it is continuous at 0, but this function is not differentiable. So the differentiability implies the continuity, but continuity does not imply differentiability. So if the function differentiable, it will be 100% continuous. But if the function continuous, that doesn't mean this function is differentiable. And the example is y is equal absolute value of x. This function is continuous at 0, but it is not differentiable at 0 because it has a corner.